All right, so this is our last section today. We're talking about improper integrals, and this will be your last one before the final. We'll talk about limits a little bit, so that could be useful as a review as well. We'll also talk about the applied problems. We'll look at that and pick out how much money you guys need to be set in your retirement. So we'll talk about that too. So first, these improper integrals have infinity in them, not just some integer. And the way that you're going to evaluate that infinity is you pretend like it's just some b. Go ahead and find the integral, integrate, and then plug in infinity. So some of these exist, some of them don't. And if you think about it, if you've got one that is getting larger and larger and larger, okay, then you're not going to be able to add that up as it goes to infinity. But if you've got one that is getting smaller and going towards some asymptote as it goes towards infinity, then you'll be able to evaluate those. So those, the ones where the limit exists, converge. So there's a converge, and we say that those are convergent. And if the limit does not exist, then we say that those diverge or are divergent. And then here's two examples down here at the bottom. This one converges. Find the antiderivative of that. This is going to be something that's getting smaller. You can find it from 1 to infinity. If you do the antiderivative of this one, you're going to get a natural log. And that natural log is going to keep bigger, something that we cannot evaluate, so it diverges. All right, so what we're going to do is evaluate this from like 0 to b. And then later we'll plug in infinity as the limit approaches b later. So we're going to do the limit as b approaches infinity of 4e to the negative 2x dx. So just integrate that, which is going to give you the same thing divided by negative 2. So that's the limit. We gotta write our limit every time to be official in notation. So if I do the same thing and divide by negative 2, then I would get a negative 2. So negative 2 e to the negative 2x from 0 to b. So when it comes to evaluating that, I'm going to plug in, come down this way, limit as b goes to infinity, plug in b. Well, that gives me negative 2e to the negative 2b minus plug in 0, which if I plug in 0, anything to the 0 power is going to be 1. So it's really 1 times negative 2. So minus a negative, well, I'll go ahead and write that, minus a negative 2. So it's going to be plus 2 on that. All right, so we know that as b approaches infinity, we got to see what's going on. Well, this e to the x, as it gets, with being the negative there, as it gets smaller and smaller, this is actually going to go to 0 as this limit gets bigger and goes to infinity. As b gets larger and goes to infinity, that's actually going to go to 0. So this ends up being 0 plus 2 when we plug in infinity in there. So this one goes to 2 and it converges. All right, moving right along. Same deal, let's determine if this one converges or diverges. So if we go limit as x well, as b approaches infinity, 2 to b. All right, so that will be, let me go ahead and integrate. So when we integrate that, we will add one that's a -3. So when we add one, that would be a -2. And then we would divide by -2, which would give us a -2 over 2 would be 1 over x squared from 2 to b. All right, so when we go plug it in, limit as b goes to infinity of plug in b, -1 over b squared minus -1 over 2 squared, which is 4. Well, as you go to infinity, this is going to get smaller and smaller and smaller and smaller for b. So it's going to go to 0. So it's 0 plus 1/4, 1/4 converges. All right, a couple of definitions here. If you have a negative infinity, then again, you just put in a, evaluate the integral, plug in the limit as a goes to negative infinity. If you had one like that went from negative infinity to infinity, then c could be any real number, so you usually want to pick something that's going to work out easily for us. I don't think you would get one like that on the test. The ones on the test are going to be more likely to be one like this, or one that we just saw. And by the test, I mean the final. You'll have one of these on the final. There's no Chapter 5 test. Okay, accumulated present value. So this is pretty good. This formula from 0 to infinity of p equals -k to the t, so kind of like your PERT formula, PE to the RT formula, where k is our rate. It just so happens that it's easily evaluated to p over k. So you don't have to do calculus so much, but know that this is being derived from calculus principle, which is a improper integral. And this is going to be where k is the rate compounded continuously. So what the heck does that mean? Well, if we know what we wish to accumulate present value means what we wish to pull off of an investment each year, then you can determine what rate you're going to have, and you can figure out how much money you're going to need in that investment. So just remember this p over k as we flip the page here. So how much money would you have to have chunked away in order to pull off $2,000 a year? Let's pause. All right, the announcements are over. So if we want to pull $2,000 a year, and we are assuming that we can get 8% continuously, how much money do we need to have to pull off $2,000 a year and still maintain our investment? So, in other words, perpetually means you could keep doing it forever. Well, you just have to do 2,000 over 8%, which gives us 1 by 8, $25,000. So what it's saying is if you have $25,000 in the bank account, you could pull, and you could earn 8% interest, you could pull $2,000 off of that every year, and at the end of the year, it would have made enough money to get back to where you need to be. So we could actually use this. If you know how much money you need to live on per year, and you know about what interest rate you could conservatively get, then you could determine how much money you need in your savings or nest egg to be totally financial free, so to retire, quit your job, never have to work again. So let's say Coach Kate feels like he needs $50,000 a year to live on. Not too extravagant. Living a simple life. And I am confident that I'll be able to get, I'll go kind of conservative here, 6% in my investments. How much money do I need to have saved up if I'm only going to spend that, and I've got a pretty conservative interest rate for the stock market? Well, I still need quite a bit of money. I need $833,333.33. So, doesn't look like I'm going to be quitting teaching math anytime soon. But yeah, so you can play around with this. Might give you some life goals of how much you're going to need to save in your retirement in order to pull off the amount of money you think you can get with a given interest rate. All right, here's another one. It says if you want to get $10,000 per year, so it should be less than the last example we just made up. 10K divided by 6%, $166,000 and 66 cents. Okay, so that's a pretty easy formula. It's just P over K, but it's derived from some calculus principles of an improper integral. All right, so before I cut you loose, I didn't do an example of one that diverges. So let's pull up an example of one that diverges. Can slap that on the end here. So let's say we have an integral from 4 to infinity of dx over x. Well, first, I'm going to write that. Well, we'll go ahead and do the limit thing too. We'll say, well, that's the limit as b goes to infinity of 4 to b, and I'm going to write this as 1 over x dx. And you guys will recall from the test that you just took that a 1 over x integrates into a natural log of x. So the limit as b goes to infinity of natural log of x from 4 to b. So that yields us natural log of b minus natural log of 4. But as this goes to infinity, well, it's actually just going to keep getting bigger. But the limit as b goes to infinity of natural log of b does not exist because it just keeps getting bigger and bigger and bigger. So since this limit doesn't exist, wait, I need to put a natural log in there.